Right. I hope you understand. It's simple thing to understand. So we need to maintain this pressure and this temperature in reactor. Can anyone say how do you maintain this? The reaction is carried out at this pressure, at this temperature. How are we ensure these conditions in the reactor? By supplying reactants at this condition. We ensure these conditions. How are we ensuring these conditions? By supplying, especially pressure, in the form of, if we supply reactant at that pressure will be maintained in the reactor. So, first of all, the reactants like N2 and hydrogen is compressed to 200 atmosphere. Is compressed to 200 atmosphere. After compression, after achieving the desired pressure, of 200 atmosphere, the reactants undergo through or pass through a heat exchanger. Reactants are passed through a heat exchanger, where the reactants are being heated from normal whatever temperature after the compression to 675 to 700 Kelvin degree centigrade temperature. So reactants are supplied at a stoichiometric ratio. Later on, I will tell you how to get this because we don't have nitrogen and hydrogen naturally available anywhere. But how are we getting this? And we will discuss later. Okay. For time being, we assume that we are able to get this ratio. How are we getting this ratio? How are we getting this speed? That I will explain later part of today's class. Okay. So first you can, for time being, assume that nitrogen and hydrogen is being supplied at a ratio of 3:1. So this reactant mixture is compressed to 200 atmospheric pressure and heated to 675 to 750 Kelvin temperature is supplied to this reactor. So here we have a sprayer that distributes across the support plate so that you get the reactant is flowing throughout the reactor uniformly. We have a uniform spray system, distribution system that will ensure the reactants to spread across the top distributor plate so that the reactant can flow over the reactor uniformly. In any heterogeneous catalytic reactions, in any heterogeneous catalytic reaction, the reaction takes place on the surface of catalyst. Reaction takes place on the surface of catalyst. The catalysts are often porous catalysts. The catalysts are often porous. On the porous surface, we will have the active sites or active centers. On the active centers, what will happen is the reactant diffuses onto the catalyst surface and adsorb onto the catalyst surface. The reaction happens on the catalyst surface, then products dissolve from the catalyst surface and again comes back. So these are the 6 steps happens. I'm sure you know in the reaction engineering course, you would have learned that in heterogeneous catalytic reaction, how the reaction takes place. Here, I have just kept a graph how the ammonia content varies with respect to temperature. Same graph which I shown earlier in the previous slide only, the temperature versus conversion. But in the previous graph, in y-axis we have ammonia content, in x-axis temperature. But here I am showing temperature in y-axis and ammonia content in the x-axis. So here, this is the equilibrium curve, and this is the maximum rate curve. Maximum rate occurs at these temperatures for this ammonia content, and this is the equilibrium curve. We prefer to operate at the maximum rate curve than the equilibrium curve. Why? Because at higher rates, we have the lower residence time. When you have the lower residence time, processing cost and the fixed cost of the process vessels becomes lower because we have the higher faster reactions requires lower residence time. Lower residence time means volume of reactor is lower. Volume is lower means the reactor size is lower. That benefits the both maintenance, operating, and construction cost of the reactor. So we operate at maximum rate than the equilibrium. Of course, both are similar, both are close, then it is fine. We can operate either equilibrium or maximum rate. But when we have a significant difference, we prefer to operate at maximum rate than the equilibrium. So when the temperature increases, the conversion increases. That's what this line shows. When the temperature increases, the ammonium content increases. So this is what happens, as the reactant enters into the reactor, reaction starts. As the reaction proceeds, one thing we observe is rise in temperature. One thing we observe is rise in temperature. Can any student guess why the temperature increases? Why the temperature increases as the reaction proceeds? As the reactants comes downward, the reaction happens. As the reaction proceeds, the reactant's temperature increasing. Anyone tell me what could be the reason?
Exothermic reaction.
Yes, it is an exothermic reaction, hence the temperature increases. As the temperature increases, it touches to the maximum rate curve. It touches to the maximum rate curve. If I proceed, if the temperature goes forward, what will happen? It will touches the equilibrium curve. It will touches the equilibrium curve. If once we achieve equilibrium, can the conversion can be increased? Can conversion be increased beyond this? Will it be possible to go beyond this? After reaching equilibrium, will it be possible to go beyond this? Any idea from students or any guess? Not possible because equilibrium means that is the maximum. We cannot go beyond this. We cannot go beyond this. So, do you prefer to operate at this dotted line or at this line, solid line? Any guess from the students? Do you prefer to operate at the dotted line or do you prefer to operate at the solid line?
Dotted.
Dotted line. Right. Now, keeping this, maintaining this. Now, how do we improve the conversion? This way, we are getting only 10%. This way, in no time, we are getting only 10%. But if you wanted to improve this conversion from 10 to 25 or whatever, how do we do this? Can you just quickly think about it? Now, at this condition, at this setup, we are once we reach to 700, whatever, we can only get at best of 15% or 16%. But if we wanted to go beyond 20%, how do we do this? How to achieve this? So here we don't want it, we don't want the temperature should go to this point, because if it is crossing maximum rate curve, you know, if crossing maximum rate curve, even though we achieve equilibrium curve, but the rate is lower, so we don't prefer. We don't prefer to go to temperature beyond this. We don't want temperature to go beyond this. So, but if let the reaction happen, the temperature will go above this. Now, how do we control? How do we control this temperature? Let's say, what should we do after reaching this temperature? If you don't want further rise in temperature to happen, what we should do? Let's say we start, let's say we reactants entered, reaction proceeds, temperature increasing. And we recorded and temperature come to 700, then we wanted to stop it. What should we do? Any quick thought?
Coolants.
Coolant. So how do we cool?
Supply cold water.
What way? In the reactor? Can we
Plus
supply
jacket.
the jacket? Now, so we have circulate around this. Now, will it be possible? See, this is a huge reactor, the huge packed bed reactor, and this is you see this is operating at 200 atmosphere. That means it has at least few centimeters of thickness will be there. Few centimeters of thickness material. If you circulate around this, what will happen? Can inside here at the center point, can it get cool? Yeah, your guess is really correct that we need to circulate with cold water. But now, if you have packed bed reactor, the practical difficulty is that, especially high pressure reactor, when the thickness of this reaction vessel is higher, if you circulate it, only this outer edge, only the outer edge may get cooled down, but the inner one will not get cooled down. Am I right? Do you agree with me? It is difficult to cool down the whole thing through circulation when we have a big packed bed reactor. Do you agree with me? So, normal jacketed cooling is not will not work when we use this big packed bed reactors. Yeah. So if you use a packed bed jacketed vessel like this, jacketed cooling water circulation not possible, not practically possible. So that's why two types of cooling is recommended. This graph, from this graph, we can understand that we need to cool. We need to cool. But jacketed cooling water circulation will not work because this is a huge packed bed reactor. So two types of cooling is recommended. Direct cooling or intermediate cooling is recommended. There are two types of cooling is recommended: direct cooling or intermediate cooling. So first we will see intermediate cooling. Here, as shown in the previous slide, nitrogen and hydrogen at a stoichiometric ratio is compressed, then heated to required temperature, then supplied. Supplied. This is the same graph which we see in the previous slide. So the position 1 is the entrance. The reactant is entering into the reactor. Reactant is entering at a reactor at the position 1. Just don't quote me exact numbers, okay? Just to illustrate, I have just kept the number. So it's entering at 1 as the reaction proceeds, as the reaction happens, because of the exothermic reaction, the temperature increases. So increase from zero point 0.1 to zero point 0.2. So we know that at zero point 0.2 it reaches the maximum curve. So we need to cool down. We need to cool down the reactant to achieve this maximum conditions. To achieve this maximum conversion or maximum rate conditions, we need to cool down. We need to cool down. So is the packer bed has instead of one big packer bed reactor, it is divided into multiple beds. It is divided into multiple beds, and between each bed there is space for cooling water circulation. So we have a heating coil. There is a heating coil is placed between this, and through that heating coil and cold water is circulated, so that the whole area inside the reactor is filled with the cooling water circulation and heating coils, so that everywhere every reactant or every portion of the reactant can get cooled down. So in case of external cooling water circulation, that will not be possible for a packed bed reactors. So once you cool down, again the temperature drops. Again the temperature drops. Then we can introduce into the again packed bed reactor. Why are we introducing? Only reaction happens on the catalyst surface. If no catalyst present, no reaction will happen. So again we introduce into the that's why zero point 0.2 to zero point 0.3, zero point 0.2 to zero point 0.3, same conversion. Ammonia content is same, no change because no reaction is happening. Only just cooling is happening. Only just cooling is happening. So the just temperatures drop down from this temperature to this temperature. So only temperature reduction is happening. No reaction is happening. So at 3, at position 3 at point 3, the reactants, the cooled reactants and products enter into the reactor. Again, enter into the catalyst bed. As soon as they enter into the catalyst bed, what will happen? The reactants reacts and produces ammonia. So ammonia conversion again increases. Ammonia conversion again increases, and since it's exothermic reaction, again temperature increases. So at point 4 again it reaches the maximum rate curve. At point 4 again it reaches the maximum rate curve. Since reach maximum rate curve, again we need to cool down. Again we need to cool down. So again there is spacing between bed to bed. In that again in the space we have the heating coils through which cooling water is circulated, and the reactants and products are being cooled. So once again, keeping the same ammonia content because no reaction is happening, the temperature is dropped. At position 5, again the reactant is entered at the reactor, and again it touches the maximum rate curve. This way, through the intermediate cooling, by maintaining the maximum rate conditions, the conversion is increased beyond 20%. The conversion is increased beyond 20%. Sometimes I just shown only 3 beds here, but often there will be multiple more beds where the conversion can go up to 30%. The conversion can go up to 30%. So this is the intermediate cooling method used in ammonia reactor. Intermediate cooling method is used in the ammonia reactors. Hope you all understood, students, how this intermediate cooling is done in these ammonia reactors to get better conversion rates to maintain the maximum rate conditions. So the products leaving the reactor, products leaves the reactor at 700 Kelvin, and this goes to condenser. This goes to condenser to cool down. This goes to condenser to cool down. So now if you can see here, if you can see here, initially the reactants are being heated. Initially the reactants are being heated. Now we are also doing that intermediate cooling. We are also doing the intermediate cooling. We are doing the intermediate cooling. That means something is being heated, right? In intermediate cooling step, something is being heated. And here cooling water is circulated, and here we have heater. So here heating is taking place. Here heating is taking place. Heating is taking place, and here cooling is taking place. Here cooling is taking place. So when you have a heating and cooling, in a normal one, we have to use a steam, an external utility to heat the reactants. We again use external utility cooling water for the cooling. So if we combine these two, if we integrate this one and this one, we can reduce the external utility requirement. We can reduce the external utility requirement. So, this is the heat integration usually done in industrial reactor. Industrial reactors, this heat integration is usually done. So instead of hope you're understanding. So so this is the feed. This is the feed compressor where ammonia and nitrogen, hydrogen are supplied at stoichiometric ratio. Previously we have heater. But instead of an external heater, external heat exchanger, whatever hot gases coming from like you see here, the products leaving at 700 Kelvin. You can see here the products leaving at 700 Kelvin. The products are leaving at 700 Kelvin. Now this temperature has to be decreased, condenser. So the products leaving the reactor, the third bed. So you can see the third bed. These are the products. The whatever red color highlighted one are products. At what temperature they are leaving? The temperature here is 700 Kelvin. This is a hot stream, right? This is a hot stream. Now this is the feed, which is the cold stream. The cold stream. The cold stream. When you bring the cold fluid and hot fluid contact to each other, what will happen? Heat transfer will happen. When you bring cold fluid and hot fluid contact each other, heat transfer will happen. So that way the temperature of reactants can be improved. So you can see a clear, very clever mechanism they employ in industrial reactors. So the feed is introduced at the center pipe. Now then we have two streams are divided. Some gas goes into left hand side, some gas goes to the right hand side. Here we have intermediate tubes. Through this is red colored tubes, or through these tubes the products are leaving. Through these tubes products are leaving. So this is, you can see like a heat exchanger, baffles, and circulation is happening. So the reactant is being circulated through this. The reactant is being circulated through this, and it will flow over this product pipes. The flow over the pipes through which products are flowing. So that way the heat transfer is taking place. This way, by this heat integration step, the feed heater can be avoided. The feed heater can be avoided. This is one way. Intermediate cooling is one way. Is there any other way we can cool that is direct cooling. Is there any other way we can cool the reactants in the reactor is direct cooling. So direct cooling is possible when we have, if the gases can be quenched, if the gases or the reactants, if the reactants can be quenched by any other form. Let's see what are the typical direct cooling technique used here. Then I will give you some general conditions. So, so this is the packed bed reactor. This in this packed bed reactor, this instead of whole one single bed, they are divided into two beds. Previously, we have seen one complete bed. Instead of that, that is divided into two beds. One in the left-hand side rectangular block, and the other one is right side rectangular block. And here you can see these are the product is coming this way. The product streams are coming. The red pipelines which shows the products are coming, and through this first bed and second bed, the products are coming, and all are joined together and sent outside. All are joined together and sent outside. So this is the whole packed bed reactor. This whole packed bed reactor has two small beds, and we also have the heat integration step. We also have the heat integration step. So we have, when you want to do heat integration, like just now explained in the heat integration step, the product's heat is being utilized for the rise in temperature of the feed. The product's heat is being utilized. The product's heat, the heat is being utilized to rise the temperature of the feed. So here we wanted to maintain the heat integration, right? So we introduce instead of introducing at the bottom the reactant gas and introducing at the top. I will tell you why in a minute. So we have N2 plus H2 at a stoichiometric ratio, compressed and introduced into reactor. Compressed and introduced into the reactor. When you introduce in the reactor, what will happen? This everything is sealed. This whole portion is sealed. So the gases are forced to flow through. The gases are forced to flow through this. The gases are forced to flow through this. So they will straight away come down. And you know, this is also hot reactor, because here also exothermic reaction is happening. Here also exothermic reaction is happening. So this is hot. So when the gases circulate, flow over this also, some heating will happen. Some heating will happen. That's why it's being introduced at the top rather than the bottom. So the reactants flows down and come downwards and flow over this pipelines through which the product is flowing. So here, this is the product line, and hot product is going out. So when the cold feed reactants, the cold reactants flow over this product, the pipelines through which product is flowing, the heat transfer is taking place. That way, the reactants are being heated. Now, after heating, again it goes through this, and again, while it is traveling through, heat transfer takes place. Heat transfer takes place. So when it is turned to blue to green, that means becoming the hot and required temperature. It's the hot and required temperature. Required temperature is around 675 Kelvin that we have seen earlier. So after once it passes through, it enters into the catalyst bed. Enters into the catalyst bed. So as the catalyst in the as reactant pass through the catalyst bed, what will happen? Reaction happen on the catalyst surface, And when the reaction happens on the catalyst surface, temperature in the reactor is increasing, temperature in the reactor is increasing. Now we need sort of cooling. So the here cooling is done by spraying quench gases. By spraying quench gases. So ammonia, nitrogen, and hydrogen can be quenched, means can be cooled down to very low temperature and made into liquid. Can be made into liquid, or you can keep into you can you can get almost like minus 10 degrees centigrade, still maintain as a gas, still maintain a gas. So that cold gas is sent to a small pipeline. There is a small pipeline inserted in this beds, and we have a nozzles here. We have a nozzles here. This cold gases can be this cold gases is sprayed at intermediate level. The cold gases is being sprayed at the intermediate level. This way, it will directly cool the reactant without doing any intermediate cooling like last in the previous slide we have seen. So this way, the quench gases are sprayed in between at different points to cool the to reduce the temperature beyond 700 degrees centigrade. To reduce the temperature, whenever there is a rise in temperature, to reduce it, the quench gases is sprayed. The quench gases is sprayed. So this way, they're able to maintain conditions such that the temperature doesn't cross the maximum rate curve. The temperature doesn't cross the maximum rate curve. So direct cooling is can be used if the reactant gases can be quenched. If the reactant gases can be quenched, the direct cooling method is preferred or can be used. If quenching is not possible, that is cooling while maintaining in the gaseous form, we have to use the intermediate cooling. So that is previously I have shown one, and there is another possible mechanism. Here, this is the bed 1, bed 2, bed 3, and here we have a small pipeline. See, small pipeline which is going through this. They spray this cold quench reactant through this for the intermediate cooling. So what next? What next after the reactor in this? So now I think I spent good amount of time to make you understand what are the how the reactor, what is the configurations in the industrial reactors. Probably you understood. So what happens? What next after the reactor? What next after the reactor? So we got nitrogen hydrogen sent to the reactor. Now the ammonia is being produced. What happens after the reactor? So students will take just 2 minutes break, 3 minutes break, because I just want to drink some water. So you also may drink some water and get ready. Yeah, thank you. Thank you for being online. I don't know why only 30, 35 students are joining. So, so we have seen reactors. Now we have seen how the intermediate cooling enhances the conversion. Regardless of all these, at best conversion of ammonia can be achieved between 25% to 30%. That means 70% of the reactants are unused. So 70% of the reactors are unused. So what should we do? What should we do? So since the conversion is very low, whenever whenever we don't achieve complete conversion, or rather we can say whenever we achieve low conversions, the immediate step after the reactor, the immediate step after the reactor, you can see immediate. That means immediately after the reactor, we need to separate the unreacted reactants. We need to separate the unreacted reactants. In this case, unreacted reactants are nitrogen and hydrogen. Unreacted reactants are nitrogen and hydrogen. So these two unreacted reactants needs to be separated from ammonia product, and these unreacted reactants should be recycled back. These unreacted reactants should be recycled back. Then only we can avoid the loss of nitrogen hydrogen. Then only we can avoid the loss of nitrogen hydrogen. Also, we can get the higher yields while keeping the conversion low through the recycling. We can enhance the yield of ammonia. We can enhance the yield of ammonia. Yield refers to the amount of ammonia produced by the amount of reactants reacted, or amount of reactants supplied. Through the recycling, although we are supplying less nitrogen hydrogen, since we are recycling back major quantity of nitrogen and hydrogen, we can get the more yield. I'm sure you learned these things in your chemical process calculations, how the recycling enhances the yield while keeping the conversion low. Sorry. So feed the nitrogen and hydrogen supplied at a 3:1 stoichiometric ratio. Often in industrial processes, if you have any water, if you have any water particles, either during compression or initial process, if you have any water particles present, they will be removed. They will be trace amount of water particles, anything is removed because that is poisonous to the catalyst. That is poisonous to the catalyst. So this filter removes any oil droplets, mist particles, anything is present in this nitrogen hydrogen mixture. Like here we have super absorber kind of filter. They just traps this oil droplets, the water droplets present in this gaseous mixture. Then it undergoes to reactor, packed bed reactor. Just now we have seen either intermediate cooling or direct quenching. In this process flow diagram, we won't show that. In the typical process flow diagram, we won't uh, show that intermediate cooling or quenching. So after leaving the reactor, after the leaving this reactor, we all know that it's being introduced at 200 atmospheric pressure, 200 atmospheric pressure, right? 200 atmospheric pressure. So at that pressure it is being sent. Considering minor loss of friction, there could be very small losses in the pressure drop, but still you will see the pressure is almost 190 atmospheres, 190 to 190 atmospheres of pressure is comes here. So the pressure is released after coming out from reactor. After coming out from reactor, the pressure is released, decompressed. The pressure is this is expander because the decompression is also called expander. The pressure is released. The pressure is released to normal temperature. The pressure is released to normal pressure. Normal pressure. So here, what are the things present in the outlet of the reactor? We have unreacted nitrogen and hydrogen. We have unreacted nitrogen and hydrogen, and we have ammonia, the product. After leaving the reactor, we have unreacted reactant, nitrogen and hydrogen, and we have product ammonia. So here we need to separate them. We need to separate them. So for the separation, there could be multiple separations possible, but here one clue is given. One clue is available that at 1 atmosphere, the condensation temperature of nitrogen is minus 183 degrees centigrade. The condensation temperature of hydrogen is minus 252 degrees centigrade, whereas ammonia condensation temperature is minus 33 degrees centigrade. So, if I want to separate ammonia from nitrogen and hydrogen, what should I do? Any guess from the students? Based on this clue, if you want to separate nitrogen, hydrogen, unreacted reactants from the ammonia, what I can do? What can we do? I can say.
Liquefy ammonia.
How? What temperature?
Minus 33.
Yeah. If you liquefy all the three gases at minus 33, which one will become liquid? Ammonia will become liquid. Whereas nitrogen and hydrogen will be remain as gases because the condensation temperature is much low. That is why I said nitrogen and hydrogen can be used as a quench gases because they can be remain as gases even at very low temperature. So liquefaction or condensation takes place in a condenser. I'm sure in heat exchanger you have seen, you have heard about condensers. So after condensation, we are doing the condensation temperature close to ammonia, that is minus 33. So roughly it will go up to almost minus 35 degrees centigrade. So here we have liquefied ammonia and gases, nitrogen, hydrogen, are sent to the decanter, gravity settling chamber, where gases and liquid is separated, and the liquid ammonia, the liquefied ammonia is removed as a product. The liquefied ammonia is removed as a product. Ammonia goes to ammonia storage tank. Ammonia goes to the ammonia storage tank. These unreacted reactants, the gases are nitrogen and hydrogen. So these two are the unreacted reactants are recycled back. Now here we have released the pressure, right? We have passed through the expander, we have released the pressure. So we have to, before we mix it, we need to compress it and mix it back. Before we before we recycle it back, we need to compress to the required pressure and mix it. But sometimes this ammonia synthesis plant will have some purge stream. Ammonia synthesis will have a purge stream. The reason for purge stream is this nitrogen hydrogen feed gases will contain some impurity called argon. Impurity called argon. The source of argon and all we'll discuss a little later. So this argon impurity, although this is in trace amounts, if you do major amount of gas are being recycled, so there is a high chance of accumulation of this inert. This high chance of accumulation of this inert in the reactant is possible. Hence, some of these unreactant reactants is taken as a purge stream. Very small quantity. The purge stream is primarily to reduce the accumulation of impurities present in the feed nitrogen and hydrogen gas. Feed nitrogen and hydrogen gas. So this is the process flow sheet of ammonia. Ammonia process plant is very small and simple. It has a compressor, expander, heat condenser, and simple gravity separator, that is decanter. But the major heart is reactor, and in the reactor the cooling system is more critical, and I hope I have given a required amount of details for you to understand. So ammonia plants are everywhere, not only in the fertilizer industry, it is also there in most of the refineries. So you can, if you get a chance to visit any refinery, you can see. Probably this explanation can help you to understand the system better and understand better. So hope you are understood ammonia production process. If you visit the ammonia industry, it looks like this. You will have a compressor, then you will have a filter, then you will get to see a big reactor, then you will see an expander, then you will get to see a condenser, then you will get to see a decanter. And of course, we have a feed storage and product storage tanks. So this is the process flow diagram of ammonia production process. In a normal offline mode, in an exam, we will give a question like draw a process flow diagram of ammonia and explain the detail. You're supposed to draw this diagram and write various highlights of the processes. But now that we don't have that offline mode of exam, so whatever reasonings I have explained yesterday and today, that I will give as a small questions. Like, for example, how do you separate unreacted nitrogen hydrogen from ammonia? You will have to write condenser at a temperature of -35, like this question and answer. And why are we purging the unreacted reactants? You will have to say to reduce the accumulation of inert argon gas present in the feed. So why are we using the intermediate cooling? Like these questions, or what are we achieving through intermediate cooling, higher conversion rates, and also ability to operate at the high rate than the equilibrium line. So like these small questions will be asked and you need to answer. Hope you got an idea. what kind of questions are expected from these type of classes. I have told you offline and online what are the differences. Ultimately, you need to study same, only way the different way of we ask the questions. So sometime I will just put uh, like partial flow diagram and I'll ask the fill what comes in this. So that way you can just write what unit operation will come, missing unit operation. You can also mention, you will be mentioned there. So these small ways, different ways and means to evaluate the student, we are using it. Any questions before I move on, students? Are you able to understand whatever I'm explaining so far? Will it be, is these details? Another important question I forgot to ask in last class. In the mechanical operations feedback, some students told that I'm teaching very slow. Is my speed is okay or slow? Do I need to go faster? Can you guys give me input? And the feedback of mechanical operations. Only feedback I got that I'm teaching very slow. If, forget about that course, but in this course, am I teaching at the right speed or I'm also still slow?
No, sir, it is at the right speed only. We can understand.
Okay, okay. Others also feel same. If any student feels that I am slow, if you hesitate to tell in this forum right now, you can message me which parts I am slow or whatever. That way I can avoid that minor negative comment. Okay, thank you. So we'll continue, assuming that no questions. So one important thing I wanted to also say, while I construct this flow sheet, I have logically explained each and every intermediate connections. The reason for explaining everything in so detail so that you should not by heart it. Rather, you should remember why first is coming, why then second is coming. Each and everything I am giving an explanation for each and every process. Before each and every arrow, why this is arrow moving this way. All the thing I have given a reason so that you understand and keep that in your mind. You don't need to buy hard this whole flow sheets, but if you understand reasons, in a quick look, you should be able to understand. That is the reason I'm stating and giving good amount of details and explaining each and everything so that you should understand inherent details and you don't need to buy hard this process flow diagrams. So, how to get this N2H to feed, right? We don't have directly anywhere as a raw material N2H2 feed at a stoichiometric equation. But how do we get this N2/H2 feed? So, we need nitrogen source for the nitrogen source is air because we know that the abundantly available, freely available material to us is air and which contain nitrogen. But one big but is that from air, oxygen has to be removed. Although we can use air as a nitrogen source, but one important condition is that oxygen has to be removed. What is the source of hydrogen? The source of hydrogen is syngas. The syngas contains hydrogen, but the one important condition is that carbon monoxide has to be removed. Carbon monoxide has to be removed. So one important correction. Here oxygen has to be removed and here carbon monoxide has to be removed. So if you want to remove these two, if you can combine, if you combine these two, one thing immediately happens is oxidation between carbon monoxide and oxygen. And we know carbon monoxide is a highly reactive molecule. Carbon monoxide is a highly reactive molecule. There is very high chance of quick oxidation happens. That is why they join air and syngas. Idea is when you combine air and syngas, when you combine air and syngas, what will happen is oxidation of carbon monoxide takes place and converts to CO2. Then some partial hydration also happens. That is, hydrogen also reacts with oxygen, can form H2O, but this is less. So this way we get, once we combine air and syngas, CO2, H2 plus N2, this is the what we wanted, and we also get H2O and CO2. So from this CO2 has to be removed. How do we have a gaseous mixer. We have a gaseous mixer. We want to remove one gas component. What process we can use? Gas absorption or gas adsorption we can use. So the most commonly used method is gas absorption. If you use amine solution or sodium hydroxide, NaO solution, this liquid NaOH, a concentrated liquid NaOH, if you use CO2 reacts with NaOH and forms carbonates, that way you can separate CO2. That way you can separate CO2. And we can also remove H2O. We can also remove H2O in the same process because this is NaOH still contain water and this water is diffuses from these gases mixtures to the liquid level. If not, we can always remove the water vapor. This way, by using this simple gas absorption process, CO2, H2O can be removed. That way we can get the N2 plus H2. N2 plus H2. So this is the common way to get the N2 slash H2 feed together rather than getting individual and individual hydrogen, which is very difficult. Rather, getting N2 plus H2 is more easy. Getting N2 plus H2 is more easy way. I hope you all understand. I just repeat quickly. Source of nitrogen is air. Source of hydrogen is syngas. However, air oxygen from the air has to be removed. Carbon monoxide from the syngas has to be removed. Individually removing oxygen and carbon monoxide is very complicated task. So rather more simple way is when you combine air and syngas, carbon monoxide in syngas reacts with oxygen present in the air which forms CO2. Removal of CO2 is much easier than removal of carbon monoxide. So CO2 and H2O form during the reaction between syngas and air. CO2 and H2O removed by using gas absorption process. That way we will get N2 plus H2 only. This N2 plus H2 being supplied to the ammonia reactor as a feed. Now you all know about air, but now how to get syngas? That is the question. How do we produce syngas? So syngas is produced using two methods. One is partial oxidation of hydrocarbons or biomass. If you take biomass like wood or any other biomass, if you do partial oxidation means if you have any carbon, right? If you reacts with oxygen, it forms CO2. If you give required amount of oxygen, if you give required amount of oxygen to convert this into CO2, that is called complete combustion, a complete oxidation. But if you use stoichiometrically less than what is required for complete combustion, that is called partial oxidation. So if you use instead of one O2, if I use half O2, then I will get CO. So this is less than for the complete oxidation or complete combustion. If you introduce lower amounts of oxygen than the required for complete combustion, that is called partial oxidation. So partial oxidation of either hydrocarbons or biomass will can also produce syngas. Another thing is steam reforming of natural gas. Steam reforming of natural gas also produces syngas. Also produces syngas. Little details. So whether to use most often most often they combine both. Although this is one method, this is one method. Most often the producing gas, they will do steam reforming. They will also do the partial oxidation. Both are being carried out. Why they are carried out? Both are carried out. Steam reforming is an endothermic reaction. Steam reforming is an endothermic reaction. Whereas oxidation is exothermic reaction. Exothermic reaction. Okay? So, but the quality of syngas where we get more amount of hydrogen is possible in the steam reforming. So that's why steam reforming is preferred, but at the same time we need energy. Energy needs to be supplied for the steam reforming. So that energy is generated by the exothermic reaction from the partial oxidation. So if you combine both, some amount of steam reforming, some amount of partial oxidation, that way we can mitigate the energy demand. That way we can mitigate the net energy demand. So before we do this, uh, like before they do this partial oxidation steam reforming of these hydrocarbons or natural gas, one important thing is desulfurization. Desulfurization. Why we need to remove these sulfur components? Because the sulfur components are poisonous to the catalyst. Sulfur component is the poisonous to the catalyst. So, so sulfur, desulfur, two types of sulfur components. One is H2S as a directly present. Sorry, the sulfur components, mercaptans, is present in the hydrocarbons, is removed using this reactor. The sulfur components reacts with hydrogen, reacts with oxygen in the presence of this catalyst at this temperature. That's converted to hydrocarbons and H2S. H2S is removed using the zinc oxide. H2S is removed using the zinc oxide. This way, the sulfur components are desulfurization of methane is carried out. Methane or any hydrocarbons contain the sulfur components. First of all, the sulfur components react with hydrogen and produces H2S, and H2S is removed with help of the zinc oxide. After the desulfurization, steam reforming takes place. In the primary steam reforming, there are two stages: secondary reforming and primary reforming. In the primary steam reforming, methane methane reacts with water. Steam reforming means reacts with water. Methane reacts with water, produces CO plus 3H2. CO plus 3H2. And you see, this is highly endothermic reaction. Almost 210 kilojoule per mole of heat is required. Now, whenever we wanted to carry out the dehydrogenation or hydrogenation of reactions, we need metal catalyst. Whenever we want to carry out the hydrogenation or dehydrogenation of reactor, we need a metal catalyst. Like that's why in the previous also we need metal catalyst. Here also we need metal catalyst. So nickel supported alumina catalysts are being used. Nickel supported. We need noble metals ideally, like nickel, platinum. Noble metals gives more better, but for the cost point of view, sometimes we have to use other metals also. But any metal catalyst can can be helpful in the hydrogenation or dehydrogenation reaction. So here nickel supported on alumina catalyst is used for the primary steam reforming reaction. Again, this is a catalytic reaction. Again, this is a catalytic and endothermic reaction. One important point I also forgot to explain in this ammonia. Any catalytic reaction, any catalytic reaction, any catalytic reaction carried out on the catalyst surface. What are present on the catalyst surface? On the pores? Active sites. Active sites, the activity of catalyst, if high, you will get higher reaction rates. The activities of catalysts are higher at higher temperature only. Okay, more the higher the temperature, the catalyst, the metal catalyst especially, will be more active at high temperature. Activity means what? Free valency electrons are present in those areas. The free valency electrons more present when the temperature is higher and higher. That is why high temperatures are preferred. High temperatures are preferred for the catalytic reactions. Why the reason is the catalyst needs to be active. The free valency electrons present should be enhanced. That is only possible at high temperature. That is why any catalytic reactions it is recommended. It is recommended to carry out at high temperatures. But big disadvantage is that at high temperatures the backward reaction favors. So that's why we always have to balance. We always have to balance at what conditions we get the best. So any catalytic reaction if you take, we always get a peak curve. So it will go up, activity goes high, as temperature increases, activity goes high, and the what is this favorability for the backward reaction also increases. So both goes by activity goes and backward reaction favors more. So balancing reaches a peak at some point, then other one dominates. So we should always take the peak conditions. We should always take the peak conditions. So that's why we have did the kinetic study. That peak temperatures only were taken. So why we operate catalytic reaction at high temperature? To maintain the activity of catalyst. The activity of catalyst is higher at high temperature. That is the reason, final reason for operating catalytic reactors at high temperature. So this is highly endothermic reaction. So it needs to be operated at high temperature. Because when you operate high temperature, the energy will be supplied. In the in the secondary reforming section, this in the secondary reforming section, iron oxide catalyst is used, where where this hydrogen can sometimes be again we have the again we have this reactions takes place. So this is the typical primary reforming reaction, primary reforming reactions. So this is the feed section. This is the feed section, feed where we have the methane and steam being introduced. Methane and steam being introduced. So CS4 and steam being introduced. So we have catalyst particle. Catalyst particles are these are the catalyst particles, which is where the reaction takes place. Now, now to maintain this, because this is endothermic reaction, right? It requires some energy, heat energy. That heat energy they supply by burning the fuel and air. So by burning the fuel and air, right, combustion takes place. Combustion takes place. That combustion generates a lot of heat. That combustion generates a lot of heat. That heat will be transferred to these reactants present in this reactor. That way, the I'll actually cut down many details here because this portion will be taught to you in petroleum like second part of this course, where most of the discussions by Professor Bhaskar Bahaduri talks about these processes. That's why I am not giving more details. If I explain, my time will be wasted, and he will also be not happy. So so by whatever energy demands for this tubular reaction, tubular reaction or endothermic reaction is supplied by burning the fuel in the air. So this is where we have the primary reforming takes place. Then we have the secondary reforming takes place in this reactor. So yeah, we have 5 minutes. So we have methane. Methane undergoes through desulfurization. So desulfurized methane supplied to primary reforming. In the primary reforming, another important reactant is steam. Another important reactant is steam. Right? So here in the previous slides, I just skipped. I didn't give details of secondary reforming for purpose because it will be more helpful for you to understand here. That's why I didn't talk about secondary reformer in the previous slides. So in the primary reforming, methane reacts with steam. Methane reacts with steam and produces this reaction. These reactions took place. Primary reform. Methane plus water, steam react with carbon monoxide, H2. So, so after primary reforming, we get carbon monoxide, we get hydrogen, and small amounts of CO2 also forms. Small, very, very small amount of CO2 also forms in the primary reforming. So, so here, see, this is the stream 1. This is the composition. In the stream 1, this is the composition. Now here, stream 3, after leaving the primary reformer, you can see methane is reduced from 97% to 14.13%. Methane is reduced from 97 to 14.13 percentage. And here we have carbon monoxide and hydrogen and CO2. Three are present. This is CO2, this is CO2, this is carbon monoxide and hydrogen. As I said, in the partial oxidation of hydrocarbons, more CO, less H2 forms, where in the steam reforming, more hydrogen forms. So that's why steam reforming is more preferred one for the hydrogen-rich syngas formation and more quality syngas formation. So we have carbon monoxide and uh, we have this hydrogen formation in the stream 3. Now, so here we are introducing nitrogen and oxygen air into the secondary forming. Why? We wanted to convert this carbon monoxide as much as possible. We wanted to convert this carbon monoxide to CO2 as much as possible. The reason for converting is CO2 can be separated more easily than carbon monoxide. CO2 from gas can be more easily separated than carbon monoxide. So in the secondary forming, complete combustion of carbon monoxide to carbon dioxide is taking place. Complete combustion of carbon monoxide to carbon dioxide is taking place. That is happening in the secondary forming. In the secondary forming, conversion of two things happening in secondary forming. Conversion of combustion of CO2, oxidation of CO with oxygen happening, and whatever unreacted methane present in this one, whatever unreacted methane is present in this one, that is also being oxidized. That is also being oxidized partially. The partial oxidation of methane also taking place. Partial oxidation of methane also taking place. These two are happening in this secondary reformer. Because oxygen we are supplying from the air, that oxygen being replaced by the combustion of CO and oxidation of methane. These two are happening in the secondary form. So this is the stream 5. You can see here methane quantity is very very low. Of course we can never get complete conversion, so some amount of methane will always present. So methane is present, and you can see carbon monoxide is decreased to very small quantity. CO, CO2 is higher, and you can see the hydrogen 59.85 and nitrogen is 20. And this way, this is 3 is to 1 ratio. Sorry. The here we have, yeah, 3 is to 1 ratio we could achieve by this after the secondary forming. After the secondary forming, we could get the 3 is to 1 ratio. 3 is to 1 ratio could be achieved. Now here, you can see here argon. You can see here argon 0.28% because this argon is present in the air as a inert material. This along with the air stream, the inert argon is entering into this. Inert argon is entering into this N2H2 post process stream. And we cannot separate this argon from air because it's very very small quantity. Separating a trace quantity materials are energy expensive, very very difficult. Hence, they will not remove it. So, so in this stream we have predominantly nitrogen, hydrogen. In this stream we have predominantly nitrogen and CO2. Nitrogen, hydrogen, and CO2. Other small quantity, small amount of CO are there, small amount of C4 is there. So here this gases stream is supplied to a gas absorber. Here we use any alkali solvent. I just explained in the previous slides. And we all know that NaOH, calcium hydroxide, they can absorb CO2 very well. So this alkali solvent is used and remove CO2. In that way, we can get N2 and H2 at 3 is to 1 ratio, at 3 is to 1 ratio using this primary and secondary reformers. In the primary reformer, methane is converted to syngas, and in the secondary reformer, remaining methane is oxidized and carbon monoxide is oxidized to CO2. That way, we converting complete carbon monoxide or major portion of the carbon monoxide to CO2, and CO2 is removed with help of alkali solvent using the gas absorption. That way, we could get N2H2 as a feed to the ammonia process. So, so this is the synthesis loop. This is the complete typical flow sheet. This is just now I showed you primary reformer. So this is the primary reformer, fuel, air. This is the primary reformer. I will talk about this flow sheet in the next class as time is going. Then we have the secondary reformer where uh, conversion of carbon monoxide to combustion of oxidation of carbon monoxide to CO2 and conversion of remaining methane to syngas is taking place. Then we have this absorption columns for the CO2 removal, right? And then we have the ammonia plant, then we have ammonia reactor and everything. So this way, this ammonia synthesis is small, but getting N2H to feed is also a big process. That's why as I said, refineries, often refineries contain this ammonia because nitrogen hydrogen, major portion of nitrogen hydrogen is coming from refineries. So they often have this ammonia recovery plant or ammonia synthesis plant in these refineries. So I will talk about this flow sheet in the next class, and that gives the complete process for the ammonia process. So hope you all understood whatever I'm trying to explain. Where is this gone? Okay, students, if you have any questions, you can ask me. Otherwise, that's all from me for today, as time is over. And thank you so much for your kind attention.
Thank you, sir.
Thank you.